Okay, one more basic principle, basic ingredient that we're going to be using a lot, and we'll be almost done with our basic review. We go on to some concept tests. So, independence is a very basic statement about relationships between variables in a probability distribution. If it is always the case for some pair of variables x and y, that the conditional probability of x given y is just equal to the unconditional probability of x, we say that x is statistically independent of y. And intuitively, what you can see from this is that knowing the value of y tells us nothing about x. The probabilities are unchanged. No effect on our probability estimates for x knowing anything about y. So this is sometimes expressed in this conditional probability form, but equivalently it can be expressed in terms of the joint probability of x, y, equal to the product of the two unconditional probabilities. And going back and forth between the two forms of this statistical independence is pretty trivial. I mean, basically, if you go back to what I just showed you a moment ago, and I multiply by p of y, I'm going to get the joint probability of x and y, right? And I'm going to get the unconditional probability of x times unconditional probability of y there. So they're equivalent statements. You could think of this as the asymmetric form of writing down the expression, and this is a symmetric form for writing down the expression, but they're equivalent. So one way of thinking about statistical independence is sort of, the amount of information that you have to store in order to represent the probability distribution. So let's just say, for the purpose of argument, that these are discrete variables, x and y, each having, let's say, n states each. So a full joint probability distribution written as a table would have order n squared entries. And if we just had a completely unconstrained joint probability distribution, you could think of this as basically having order n squared degrees of freedom. I guess, minus 1 because we have normalization, but basically order n squared degrees of freedom. Equivalently, if we think about the possible conditional probabilities of x given y, again, I've got two variables in that expression, each with n possibilities. So if there were no constraints whatsoever on the form of this, then again, I have order n squared numbers to write down or store in a computer to represent this, right? So you can think of it as a table. There's, x along the horizontal and y on the vertical, and for each value of x and y, I'm going to have an entry in that table, right? On the other hand, if statistical independence was obeyed by x and y, all I have to do is write down order n numbers, actually just n numbers, or n minus 1 numbers of normalization, for p of x, and the same thing for p of y. And that's the full data that I have to store in order to fully calculate the joint probability of x and y for any possible value of x and y, right? Because I just multiply the two unconditional probabilities. So here, the actual amount of data storage and the equivalently degrees of freedom involved in under statistical independence would just be order n. Okay? So one way of thinking about statistical independence is its dimensional reduction, right? This looks like a two-dimensional object, but if it's obeying statistical independence, then it's just two one-dimensional objects is one way of thinking about it. So it basically has a computational complexity of only linear. Okay, so we've taken a two-dimensional object, squashed it down to a one-dimensional object. Okay?